Okay, guys, today we're going to look at general formation of functions. Okay, when we're looking at the general formation of functions, there's two things we want to look for, okay, that really matter. So one is your leading coefficient, and two is your highest exponent, okay? And we don't necessarily care what the highest exponent is, we just want to know if it's even or odd. Just like we don't necessarily care what the leading coefficient is, we just want to know if it's positive or negative, okay? Taking these two, just these two, will give you a very, very good idea of what the function you're working with looks like. Okay, what do I mean? Well, let's start off with a function that we're very familiar with at this point. If we were to do something like y is equal to 3x plus 2, okay? We're going to find our leading coefficient here. So our leading coefficient is 3, which is positive, okay? Next, we need to find our exponent, our highest exponent, right? So we can look at 3x plus 2 as 3x to the 1 plus 2x to the 0. Okay? What that means, our biggest exponent is 1, which is an odd number. Okay? And let's look at the general behavior of this function if we graph it out. So 3x plus 2 is going to start at 3 and then rise over run of 3. So it's going to be 1, 2, 3, 1, 2, 3, so on and so forth. Okay? Something like this. Okay, well, let's take a look. As x goes to negative infinity, so over here, it's coming from down here. It's coming from the bottom left, right? So functions like this always start at the bottom left and go to the top right. We're going to take that behavior and apply it to functions a little bit more complex than this, right? So what if instead of 3x plus 2, you had 3x cubed plus 2x minus 1? 2x squared minus x plus 14 or something like that. What can we deduce from this function? Well, all we need to look at to generally see the form of this function is this first one with the highest exponent. Okay, we're going to do the exact same thing. Our leading coefficient is 3, so it's positive. And then our biggest exponent is 3, which is odd again. What in the world does this mean? Because I'm clearly trying to show you that there's a relationship here. What do these functions share in common? Well, if we go into Desmos and graph this one out, I want you guys to see this one. 3x squared plus 3x cubed plus 2x squared minus x plus 14. Okay, let's look at the end behavior of a function like this. Well, when we go to our x values, we can see it starts from the bottom, right? Bottom left, and then ends in the top right. They have the same end behaviors. This function looks something like this, right? That's what we're looking for here, the end behaviors, okay? What do you think happens if we make one of these values negative, right? And we can start off by looking at this logic on a linear and just applying it to a cubic. So if we were to take this and instead of this being positive, we make it negative. So we're now looking at negative 3x plus 2. Look at what happens. Same intercept, but now our slope is negative. Okay? So our end behavior is completely switched. As left approaches infinity, or as x approaches negative infinity, y approaches positive infinity this time. And as x approaches positive infinity, y approaches negative infinity down here, right? It got completely flipped around. We're going to apply the same logic to a cubic function, right? So if this suddenly becomes negative, it means we did a reflection on it, right? And do you see how it completely switched around? Just reflected around, and now the end behavior is switched to match this, okay? So let's go in and form some rules now, okay? Leading coefficient. and we want to look at the exponent, okay? So we just discovered two things. If we have a positive leading coefficient and an odd exponent, we know our end behavior is going to go something like this, always, okay? Whether it's linear, whether it's cubic, whatever the case is. And this can go up to infinite exponents, whether your exponent's 5, 7, 9, doesn't matter, okay? If our leading coefficient is negative and our exponent is odd, we're going to be flipped. So it's going to go like this, where our end behaviors flip around like this, okay? Starts at infinity, ends at negative infinity. What happens now when we start looking at even exponents then? To illustrate this, we're going to look at our simplest even formula, which is y equals x squared, right? What does that look like? So y equals x squared is a quadratic. Looks something like this. Why is this behavior different? Well, functions with an even coefficient mean they always point in the same direction. If they start at positive infinity, they're going to end at positive infinity, okay? And it doesn't matter if that's x to the 2 or x to the 4. Look at what x to the 4 looks like, right? X to the 6, x to the 8. See that? It's always the same direction they end in, right? And that's what the pattern we want to see here. But look what happens when we make it an odd function, right? We have x to the 1 here, x to the 3, x to the 5, x to the 7, x to the 9, right? That behavior is what we're looking for. So we can deduce now that if our exponent is even, and in this case we have a leading coefficient that's positive, it's going to start in the top left and end in the top right, right? And just like before, if we flip our leading coefficient and leave it even, it's just a reflection, okay? So this is going to be a very helpful chart to help you visualize functions, and you will use it throughout your whole year, right? So make sure you take this note down and make sure you have a thorough understanding of it and play around with it in Desmos, right? Try to make a function with each of these, right? So essentially make four functions, one with positive and odd, one with negative and odd, one with positive and even, and one with negative and even. And just give a quick description of why it's happening, right? Okay. Good work, and I will see you on the next video.